In my previous video, I showed how the Julia set is generated. You saw that there is an infinite number of Julia sets. The Mandelbrot set is created from Julia sets. But to understand this, I will have to show you a little bit more information about the Julia sets. You can see from the examples of some of the Julia sets, and these are Julia sets, that there are two different groups. One group has black regions, where the points remain bounded, and colored regions, where the points go to infinity. The other group has no black regions, or only small areas of black that don't form a region, and the rest of the set is colored. When the black forms a region that is connected, the Julia set is then called connected. When the black spreads out and doesn't form a region, the set is then called disconnected. Sometimes it is difficult to see whether the black areas form a continuous region. So how do you know if the Julia set is connected or disconnected? It turns out that if the point 0 remains bounded, and this is in the center, the set is connected. Otherwise, the set is disconnected. So you just have to look at the origin. The Mandelbrot set uses this information. The Mandelbrot set is also plotted in the complex plane. Remember the iterative equation f of z is equal to z squared plus c, and z and c are complex numbers. For each Julia set, the c value remains constant, while the value of z is iterated through the function. A different c value creates a new Julia set. Because there is an infinite number of complex numbers, there is also an infinite number of Julia sets. Each point in the Mandelbrot set corresponds to a c value of a Julia set. If a Julia set is connected, the corresponding c value is colored black in the Mandelbrot set. You can see that when I move my mouse over the black regions of the Mandelbrot set, you see a connected set on the other screen. If the Julia set is disconnected, the corresponding c value will be given a color, depending on the degree of disconnection. You can see this here as well. I move my mouse over the colored regions in the Mandelbrot set, and all the Julia sets are disconnected. The points on the boundary between connected and disconnected sets are the most interesting. The Mandelbrot set is a fractal, to date the most beautiful fractal we have ever seen, and because it uses the information of an infinite number of Julia sets, it is also infinitely diverse. No matter how far we zoom in, you will always find approximate copies of the whole set. The Mandelbrot set contains every imaginable type of fractal, and you can recognize a lot of them in nature. Think of ferns, galaxies, lightning, and maybe even the whole universe. It has an infinite diversity and complexity in patterns, created by an amazingly simple rule. The Mandelbrot set is a mathematical universe. You can understand that, before computers existed, people could only guess what the Mandelbrot set looked like. The number of calculations is enormous. Even computers need a lot of memory. We will now explore the set. I will show you a Zoom movie made on my computer. It is best to switch to full screen, so you can appreciate what Benjamin Mandelbrot meant when he said, "Infinite wonders spring from simple equations repeated without end."